suitable for visual and photographic, although most people don't use these for photographic, not because so much of the telescope, but because of the mounting system. The mount doesn't track, and if you get a tracking mount for a scope this big, mucho bucks. The eyepiece is normally conveniently placed, whether I'm looking at something near the horizon or I'm looking something right up at the zenith. I can see this eyepiece without having to climb up on a ladder. I can sit on a chair. Very, very comfortable to use. Another advantage over reflecting. Again, it's a great choice if you want to look at faint objects that are very dark. For a small amount of money, relatively small amount of money, you can get a fairly large telescope that will allow you to see very, very faint distant objects. And they're great for the beginner because there aren't too many parts to this. One thing I did leave out is this is a fairly simple telescope. When it gets to be about 2 o'clock in the morning and you've been out in 15-degree weather, you really love this telescope because in 3 minutes it can be in your car. And so they're very simple and they're very sturdy and they last a long time. So great advantages to a reflector. But it comes with some baggage too. The mirror surfaces are prone to deteriorate because this is an open telescope. So anything that's in the air, pollen, whatever, has a great chance to end up on that mirror. So it is an open telescope and they do require some maintenance. The secondary mirror, that diagonal mirror that's in the light path, does get in the way of the light and cuts down somewhat on the contrast. Not a lot, but a little bit. That's something to consider. If you're looking at stars, very, very small, bright stars, you can see spikes around the stars. And those spikes are caused by these 4 poles that are holding the secondary mirror in place. Okay, so that will cause spikes, and it really shows up on photographs. It's very sensitive to alignment. Matter of fact, every time you use this telescope, you have to make sure that the primary mirror is aligned to the secondary mirror. Not very hard to do, by the way, fairly easy to do, but you do have to align it almost every time you use it. There's something called coma, and coma has to do with distortion. When you look at stars through this kind of a telescope, at the edges of the field, the stars start to elongate. And that's because the way this telescope is, the short focal length and the large aperture, it tends to distort the images around the edges. There are correctors you can buy. Telview makes the Paracore, but that's extra expense that you have to get to resolve the coma. And again, because it has such a large aperture and a small focal length, you have to use reasonably good eyepieces if you want to see a perfectly clear field all the way around. Otherwise, the coma is going to be even worse. And the last thing about these reflecting telescopes is because they are so large, you may have to wait a long time for the telescope to reach what's called thermal equilibrium. You really see that in the cold weather. You take the telescope out of your house, you have this very, very large glass surface that's room temperature. You bring it outside to set up. It's 35, 40 degrees out. And what's happening is as that mirror is cooling down, and we're talking millionths of an inch of tolerance here, the mirror, the way it focuses its light isn't completely equal until it reaches the same temperature as the atmosphere. You can get fans to cool them down, but the larger these telescopes get, the more effect you get on the thermal problem. Refracting telescopes, that's the oldest type telescope. This is a refractor over here. It uses a series of lenses in the front, through a focuser and an eyepiece in the back. The most common type of refracting telescope, and we all know it, is a pair of binoculars. Binoculars are really 2 refracting telescopes put together. And refracting telescopes go all the way back to Galileo. There's different designs of refracting telescopes, but they all have a similar function with an objective lens or a combination of lenses in the front along to an eyepiece in the back. Here's a couple of examples of refracting. That happens to be my 6-inch. Here's a pair of binoculars, and here's an 8-inch. One thing you'll notice with refracting telescopes, you get up to 8 inches, they get pretty big. I mean, this is an 8-inch Cassegrain. This is an 8-inch reflector. Look at the size of this 8-inch refractor. And that's just the nature of the beast because of the long focal length and the fact that you're not bouncing the light with mirrors. You start getting up over 8 inches, you're not going to be taking these things out. They're going to be in a permanent observatory. There are a lot of good examples of good reasons to have a refracting telescope. One is the optics really hold their alignment. Very, very rarely do you have to collimate a refracting telescope. There's no reflecting mirrors to maintain. I don't have to worry about the aluminized coating on the mirror deteriorating over time like I would on something like this, because there aren't any. Very, very high definition and contrast because there's nothing in the light path. You have a clear, open path from the objective right through the eyepiece. Even simple eyepieces work very well, especially in the longer focal length refractors. They're great for solar, lunar, and planetary views, and for double stars. They're really, really good because, again, there's nothing in the light path to get in the way of seeing the exact image. But there's cons, too. One of the biggest cons is we just discussed. The smaller refractors are easily portable. That's a 4.5-inch refractor. A not expensive one. It's called a wide field telescope because it's a short focal length. But again, you start getting them around 6-8 inches, they start to get very unwieldy. It's the bulkiest type of telescope per inch of aperture, as we saw with that 8-inch scope. They're more difficult to mount rigidly because of the length. One of the things, there's a scientific term called polar moment of inertia. You get something that's very, very long, it wants to wiggle. And the longer it gets, the more it wants to wiggle. So these long refractors put a tremendous amount of stress on the mount. And unless you have an extremely stable mount, you're going to get a lot of vibration. Sometimes you need filters to do astrophotography because we'll talk a little bit about color in a minute, and Scott did talk a little bit about color. Refracting telescopes, especially the cheaper ones, tend to not give the best color resolution of your images because not all wavelengths of light focus at the same distance, and unless you have very expensive lenses and more of them, you're going to start getting color variations in your images. Inch per inch, they are the most expensive telescopes, especially if you get what's called an apochromatic or color-free telescope. A high-quality 6-inch apochromat made by, say, Astrophysics is going to be up in the $10,000 to $12,000 range. It gets expensive very, very quickly. So there you go for that trade-off. Finally, we have what's called the compound telescope. And these have become extremely popular because a compound telescope can be made in a fairly large aperture, but a fairly short tube, which has a lot of advantages, which I'll talk about in a minute. There's two types of very common compound telescopes. One is called the Schmidt-Cassegrain. And the Schmidt-Cassegrain uses a combination of a spherical mirror in the back, a correcting plate in the front with a mirror facing the primary mirror, and then an eyepiece in the back. So the light comes in from the front, is somewhat corrected by this lens in the front, bounces off the spherical mirror, hits the secondary mirror, and then goes through the eyepiece. So we actually have the light coming 3 times. So you get 3 times the focal length and 1/3 the size of the telescope. That's a big advantage in many, many ways. There's an offshoot of the Schmidt-Cassegrain called the Maksutov-Cassegrain, which works in a similar way, but instead of having a fairly flat, thin corrector lens, the Maksutov-Cassegrain uses a curved corrector lens, which kind of matches the curve of the primary mirror, and then faced on the back of it is the spherical secondary mirror. What this telescope allows you to do is to separate these 2 lenses further away, so it makes the effect of this mirror can be smaller than this secondary mirror, and you get better contrast. The net result is this type of a Cassegrain is better for planets and high resolution, high contrast. This type of telescopes is much more suitable for deep space objects because you can make these a lot bigger. These Maksutov Cassegrains get very expensive after 7 inches. And up when you get around 12 inches, they get astronomical in price, where the Schmidt-Cassegrain stays very reasonable in cost. And this is an extremely popular telescope. And here's a couple of examples of first of all, the Schmidt-Cassegrain. That would be a 6-inch, that would be an 8-inch, which is what you see right there. And then we can get up to a 14-inch, which would be about this long, about like that, on a much bigger mount. And the Maksutov Cassegrain is similar. Here's the Meade 90mm ETX. Here's the Meade 7-inch Mac, and here's a 10-inch Mac. And again, you can see it's starting to get fairly large. The advantages of compound telescopes, they're very compact, they're very portable. They happen to be, if I'm not mistaken, probably, if not the most popular telescope for amateur astronomers, certainly one of the most popular, especially in the 8-inch size. The eyepiece is very seldom in an awkward position because the eyepiece on this telescope is right here, and you can visualize if the telescope moves up or down. The eyepiece really isn't going too far, so you can sit on a chair and see just about everything in the sky with a telescope like this. Very, very comfortable to use. It's great for visual or photographic use, especially with the Maxitov Cassegrains. They can be very sharp. A lot of them come equipped with computer controls because these telescopes lend themselves very nicely to what's called the go-to computerization. Once you have the telescope set up, you just punch the little hand control, tell it where to go, and it will go. That's not to say you can't have computer control with these kinds of telescopes, but this one lends itself to it very, very nicely. There's a lot of competition between Meade, Celestron especially, and now of course China with Sinta, who owns Celestron. Because the competition is so stiff in these telescopes, the prices are very good. For somewhere between, let's say, $1,300 to $2,000, you can get a fairly well-equipped, fully computerized 8-inch telescope that'll keep you busy for a lifetime if that's what you wanted to do. They're extremely easy to mount because they're relatively short. They don't require a large mount. And they're very forgiving for low-quality eyepieces because they have such long focal lengths. You can use an eyepiece that would normally distort images at the edges, but because the focal length of the telescope is so long, you can get by with very inexpensive eyepieces. You don't need the Teleview Naglers at $300–400 a pop. You can use the $50 Plassos and get excellent images. And that could be a factor to many people. It does use a large secondary mirror. As you can see, the secondary mirror on this scope occupies quite a lot of diameter compared to the total telescope. So your contrast will go down a little bit. That's something to consider. And if you drop the power very low, you start to get what's called a shadow or a blind spot. So these telescopes have a minimum power that's a lot higher than, say, a refractor or a reflector for that reason. So you don't want to use these telescopes for very low power. The larger ones can be very expensive, and any large telescope can become expensive, but you start getting up around 14, 16 inches, you're talking into the plus $10,000 and plus, so they do start to get pretty expensive. Or again, here you got 10 inches for $500 to think about. Dew can be a problem with these telescopes. That large corrector plate in the front is just begging to get wet. You go out in your driveway in the morning, your car is all wet, your windshield's all wet. Well, you can imagine what dew does to that kind of a telescope because you got that big lens just sitting up there. So normally what we do is we'll use what's called the dew shield. And here's a typical dew shield that Scott has that will fit over the front. And what that does, it kind of keeps the temperature in front of this corrector lens higher than the ambient temperature to stave off the dew. Another thing you can do is use what's called electrical dew heaters that wrap around the front of the telescope that will also keep the front of the telescope warm. Cool down times can be very long. Again, you've got mirrors. You've got large mirrors in those telescopes, and now you have a closed tube. At least with this tube, when you bring it outside, especially if you have a fan, you can blow air through it and cool down the mirror quickly. But on these on the Cassegrain telescopes, it could take hours depending on how big the telescope is, and it's something you have to think about. The last thing, which I didn't write down about a Cassegrain telescope, they have what's called a very narrow field of view. It's like looking through a straw, so you're seeing a very small area of space. So if your idea is to see large objects like the Pleiades or the Andromeda Galaxy, you have to think twice about using this type of a telescope because you're not going to fit it all in. Let me just talk a little bit about telescope mounts. A lot of people don't think about that, but in my opinion, the mount is at least as important, if not more important, than the telescope. Because no matter how good your telescope is, if that mount is not holding that telescope rock solid, your image is going to be doing this. You're not going to see anything. The other purpose of a mount, of course, if you have tracking ability, is your mount will actually be able to track the object as the Earth rotates and keep the object in the middle of the field. And thirdly, if you have computerized control, your mount can actually find the object for you, stop on it, and allow you to track it. So the telescope mount, of course, is designed to support the telescope and allow you to point the telescope accurately at the object. There's two basic types of mounts that I'll talk about, not to bore you. One is the Azimuth mount, like a camera tripod, and the other one is a little more complicated, the Equatorial mount, that allows you to track an object as the Earth rotates. The Azimuth mount. This is an Azimuth mount. It has two motions. It has a horizontal motion going around in a horizontal plane, and it has the vertical motion up and down. So there you go. You can go up and down, and you can go horizontal. Very simple Azimuth mount. It's the simplest mount you can get, and it will do the job. If you like to star hop and find objects yourself, this is the mount to do that with. What this mount will not do is track the object. You're going to have to keep pushing the scope yourself, and it won't find the object for you in its current form. However, this Azimuth mount is computerized. Even though it only goes up and down and around on a horizontal plane, the computer in this telescope will allow this telescope to find the object, and then by computer control, it will track the object by moving up and across and track that object all night. So this will do it. The other type of mount I want to discuss is the Equatorial mount, but before I do that, I'll show you a couple of, that's Azimuth, that's Azimuth, and the camera tripod. These are all Azimuth mounts. The Equatorial mount gets a little crazier, okay? But once it's set up, it's a lot easier to use. If we can visualize, this is the Earth, and this axis right here is the axis of rotation. So this would be pointing like to the North Star, and the Earth is spinning like this. Well, if we can set up our mount and have the axis of one axis of our mount parallel to the axis of the Earth, we'll be able to follow the star. This direction that the telescope moves corresponds to the rotation of the Earth. So if I sight my object that I want to see, and I turn on my little electric motor that revolves exactly the same speed that the Earth is rotating, as the object is going across the sky from east to west, and as the Earth turns, this telescope will automatically track it in this direction. Very, very smooth, very easy to do, okay? This Equatorial mount is called the German Equatorial mount. It's one of the more common types. Another type of Equatorial mount is the Azimuth Equatorial mount that is mounted on a wedge, and all this is doing is rotating the Azimuth mount to the axis that will point up to the North Star. Either one of these two will allow you to track equatorially without any further ado. Here's a German Equatorial mount. Here's an Azimuth on a wedge. A couple of accessories that are vital to a telescope. The diagonals that we use, here's a 90-degree diagonal, and you can understand why you want to use a 90-degree diagonal. What would you rather do? Look this way or look that way? You certainly don't want to have to get on the ground and look straight through the scope. So the 90-degree diagonal is used for astronomy, makes it much easier to use. There's also a 45-degree diagonal, and that's for land use, because most of the time when you're looking on land, your telescope is basically horizontal, so you don't want to have to go all the way up to the top of the scope to look down. This allows you to look on a 45-degree angle. The other thing this will allow is an upright, perfectly right to left, up and down image. This reverses the image. Most astronomical telescopes do not show images the way we see with our eye, but again, in outer space there is no up and down, so we don't really care. Eyepieces, again, that's where I said you can spend all your money, because each eyepiece will give you a different view and a different magnification level. The finder scope is important, and you'll see finder scopes on all these telescopes. And what the finder scope does, it's a low power, usually refractor, low power telescope that will, once lined up with the main telescope, allows you to find objects a lot easier. Because just to find an object in space looking through a high-power telescope is very difficult to do. Even trying to find the moon would be very difficult. But with a low-power finder and it has a crosshair, it allows you to aim the telescope and then get right on target.